So here are the answers to the MYP2 Unit 2 assignment. First question, 13 and a sixth plus 8 and 2/3. Well, the first thing I did was change the 8 and 2/3 into 4 and 4/6. That was in order to make the denominator the same in both fractions, so that they were both out of 6. So I multiplied the 2/3 by 2/2 to make it into 4/6, and then they both have the common denominator of 6. Then I split it up into the numbers and the fractions, so the 13 plus the 8 for the whole numbers, and then the 6th plus the 4/6 for the fractions. Separately adding those up, I got 21 plus 5/6, which is 21 and 5/6. Next question, 13 and a sixth minus 8 and 2/3. So again, I tried to make the denominators the same, so I changed the 2/3 to 4/6, and I got 13 and a sixth minus 8 and 4/6. But the trouble with that is, if I try to subtract the fractions, I get a sixth minus 4/6. So I get a smaller fraction take away a bigger fraction. So to deal with that, I'm changing the 13 and a sixth into 12 and 7/6. So I've basically taken 1 out of the 13 and changed it into 6/6. So instead of 13 and a sixth, I've written that as 12 and 7/6. And that solved the problem about the fractions, because now I've got a bigger fraction minus a smaller fraction. So that's 4 and 3/6, because the 12 minus the 8 gives 4, and the 7/6 minus the 4/6 gives 3/6. But 3/6 isn't the smallest possible form for that fraction, so I've changed that to 4.5 by dividing the 3/6 by 3/3. Next, 13 and 1/6 times 8 and 2/3. First of all, I made both of those fractions top heavy. So I did that by doing 6 times 13 is 78, plus the extra 1 makes 79. And then 8 and 2/3 into a single fraction. So 3 times 8 gives you 24, plus the extra 2 gives you 26. So 8 and 2/3 as a fraction is 26/3. So I've got 79/6 times 26/3. Now it doesn't matter that they have different denominators, because all I need to do here is top times top, bottom times bottom. And that gives me 2054/18. And I'd like to write that as a mixed number, so 18 goes into 2054 114 times, with 2 left over. So the answer is 114 and 2/18, which I can reduce by dividing the fraction by 2/2 into 114 and 1/9. Next question, 13 and a sixth divided by 8 and 2/3. Well, again, I can make both of those top heavy, or vulgar fractions, or improper fractions, all sorts of terms for those. But single fractions out of a single denominator, and again I did that. 13 times 6 is 78, plus the 1 makes 79, so the first one is 79/6, and again 8 times 3 is 24, plus the 2 makes that 26/3, so we've got 79/6 divided by 26/3. Now the trick for dividing by fractions is to change it to a times and then flip over or invert the second fraction. just the second fraction. So I flipped over the 26 over 3 into 3 over 26 and changed it to a times. So I've got 79 over 6 times 3 over 26. And again, that's just top times top, bottom times bottom. And that gives me 237 over 156. And 156 goes into 237 one time with 81 left over. So that's the same as 1 and 81 over 156. Now it just happens that the top and bottom of that fraction can be divided by 3. So I divide by 3 over 3 to get 27 over 52. So the final answer in its smallest possible form is 1 and 27 over 52. The next question was about writing 0.2 recurring, 0 recurring as a fraction. So I've called that x. So x is 0.20202020 with those two zeros going on forever. Now I noticed that that repeats itself every 2 digits. So if I multiply that by 100 and get 100x, I'll get 20.2020202020 with all of those 2 zeros in the same place. Now because they're all in the same place, if I take the x away from the 100x, I get 99x equals 20, because I've done 20 point all of that recurring bit minus all of that recurring bit, leaves you with just the 20 on its own. So 99x equals 20. Divide both sides by 99 to get x equals 20 over 99. So I started with x equals that recurring decimal, and I ended up with x equals 20 over 99. So the recurring decimal written as a fraction is 20 over 99. So the question about Queen Victoria. A little bit of internet research can find you the actual date she was alive. And then you can work out the number of days. So I've got 22 days for the 22 days in 1901 that she was alive. And then in the top bracket, I've got the days that she was alive during the year she was born. So 8 days in May, that's the 24th, 25th, 26th, 27th, 28th, 29th, 30th and 31st. If I just do 31 minus 24, I only get 7 days, but because I want to count both the first and last day, then it needs to be one more. And then 30 days in June, 31 in July and August, 30 in September, 31 October, 30 November, 31 in December. So those are the days she was alive in 1819. Then thinking about the whole years she was alive, well, she was alive for 81 whole years. That's all of the years from 1820 to 1900. If I just do 1900 minus 1820, I only get 80, but because I want to count the end years, the first one and the last one, she was actually alive for 81 full years. From 1820 to 1900 is actually 81 years. You can count them on your fingers if you like. So times 365 for the number of days, and then plus 20 because some of those years would be leap years with an extra day. So a quarter of the 81 years would have been leap years, and then plus the odd 22 days in January 1901. So altogether that comes down to 30,194 days, which is 3.0194 times 10,000 days. And see how I've written the 10,000 in line with the 30,194. so that I can get the right number of zeros, and I can see that 10,000 times about 3 will give me about 30,000 days. So 3.0194 times 10,000, or in standard form, 3.0194 times 10 to the power of 4 days. Next question, just some standard form things. So 3.2 times 10 to the 4 times 6.4 times 10 to the 8. So I'm separately doing the numbers and the powers. So 3.2 times 10 to the 4 as one thing, and then 10 to the 4 times 10 to the 8 as another thing. So the 3.2 times 6.4 gives me 20.48, and the 10 to the 4 times 10 to the 8 gives me 10 to the 12, because the rule is add the powers. So that's an answer, but it's not in standard form, because 20.48 is not a number between 1 and 10. So if I make that number 10 times smaller, and to compensate for that, make the other number 10 times bigger, then I get 2.048 times 10 to the power of 13. And that is in standard form. Next question, 3.2 times 10 to the 4 divided by 6.4 times 10 to the 8. So I'm just going to write that in a slightly different way as a fraction. The line in a fraction means divide, so it's really saying the same thing. But writing it like that, then I've got the numbers lined up and the powers lined up. So dividing the regular numbers, 3.2 divided by 6.4 is one thing, and then 10 to the power of 4 divided by 10 to the power of 8 is another thing. So the 3.2 divided by 6.4 gives me 0.5, and then 10 to the power of 4 divided by 10 to the power of 8 is 10 to the power of minus 4, because the rule is that we subtract the powers. So 0.5 times 10 to the minus 4 is an answer, but it's not in standard form. So I'm going to make the first number 10 times bigger, so instead of 0.5, 5. But then to compensate for that, I'm going to make the other number 10 times smaller, so instead of 10 to the power of minus 4, 10 to the power of minus 5. And I get the answer 5 times 10 to the power of minus 5, which is in standard form. The next question was about adding two standard form numbers, and the rule with adding is that, well, there isn't really a rule. So we need to work them out separately, and then just add up the two separate results, and that gave me 640 million and 32,000, which I could have written in standard form, but the question didn't ask me to, so I haven't done that here. Okay, the next question asked for some real life problems with standard form numbers. So it could have been for a very big number, it could have been that there are millions and billions of planets in a galaxy and so many galaxies in the universe, and multiplying some very big numbers to get some very, very big numbers in standard form. Or it could have been something with very small numbers, like particles, subatomic particles, and some calculation with those. But ideally, you would have given an answer or two answers, two examples involving very large and also very small numbers. Right, the next question was all about square roots or surds, radicals, different terminology you hear for the same thing. 1,800, square root of 1,800 multiplied by the square root of 2. So individually, if you try to work those out on your calculator, you see you get long, horrible decimals that go on forever. But when you combine them, you get something quite simple. And the rule is that you can combine those as a single square root. So root 1800 times 2 is the square root of 3600. And that gives a nice round answer of 60, because 60 times 60 makes 3600. With dividing, there's a similar rule. We can divide them into a single square root, 1800 divided by 2. So the square root of 1800 divided by 2 is the same as the square root of 900. And again, that's a nice round simple answer, 30, because 30 times 30 makes 900. Next question was to write some standard form numbers in ordinary form. So 3.12 times 10 to the 5. 10 to the 5 is a 1 with 5 zeros. So it's 3.12 times 100,000. And that's 312,000. And if I write the numbers in line with the number that's the one with lots of zeros, then I can ensure that I get the decimal in the right place. So by writing this in line, I can see that the number that's the answer is about 3 times bigger than the 100,000, which makes sense because I was multiplying it by a number that was about 3. So writing it in line with that helps you get the right number of zeros and the decimal in the right place. So the final answer has only 3 zeros in it. And the common mistake, of course, would be to do something with 5 zeros. Next answer, 3.12 times 10 to the power of minus 5. So 10 to the power of minus 5 is a number that has a 1 in it and 5 zeros. It's a small number and it has 5 zeros, including the one before the decimal point. So it's 3.12 times 0.00001. 5 zeros, including the one before the decimal point. So again, writing the 3 in line with the 1 before it, I can get the decimal point and the zeros in the right place. So by writing it in line like this, I can see that the 0.00001 times about 3 should give you a number that is 0.00003 and a bit. You can see that the 3 is in the same place as the 1, so it's about 3 times as big. So once again, writing the numbers in line like this in the working helps you to get the right number of zeros and the decimal in the right place. Okay, 3.12 times 10 to the power of 0. You've got to remember the rule that anything to the power of 0 is 1. So 10 to the power of 0 is just a 1 with no further zeros. So we've got 3.12 times 1, which is just 3.12. Okay, next question, 3.12 times 10 to the power of 1. So 10 to the power of 1 is just 10, or a 1 with 1 zero. So we've got 3.12 times 10, which is 31.2.